So, Bismillahirrahmanirrahim, once again, um, in the previous lecture, we discussed about the definition of the geographic information system, where geography and information system were separately uh, defined, and information system was said to be useless without human involvement. And beside that, it has some software and hardware component. The software and hardware has the capability to take input, store your inputs and outputs, uh, output itself, manipulating the input and output, also the stored data, and analysis of the input and stored data using manipulation. The geography is the change or study of the changes in the pattern and the processes that occur on planet Earth, and this all system is used for the purpose of certain decision making, and for civil engineering purposes these decisions can be for land use, natural resources, environment, urban facilities, transportation, and administrative records. We then also discussed about remote sensing, where we discussed that out of several senses, the main thing that we sense on the surface of the earth is the reflection of the light. Uh, and of course, light is then detected using a sensor called a camera. And the reflected light usually is the sunlight, but it can also be the radiation thrown by a satellite towards the surface of the earth, and its reflection is then seen using a camera on board. The visible light, beside visible light, the other frequencies that are lower or higher than the visible range, like the lower frequencies, can be infrared, microwave, and radio waves, as well as the higher frequencies above violet are ultraviolet X-rays and gamma rays and other particles. They can also be observed using these cameras, so we can uh, not only see the visible things but also the invisible phenomena like a wind movement, wind currents, also the currents of water, the movement of clouds, the global warming effect, etc. Using these observation of these lights. The uh, technology is called remote sensing because remotely we observe the surface of the earth. If we use drones, the uh, resolution of the quality of the data will be very high. Higher quality can also be achieved by using a ground-based camera. So a person holding a camera can also take a photograph on the ground. You might be familiar with Google Maps, where there is a street view. So in Google Maps, when you zoom further and you go to street view, usually a camera on the ground is used to take those photographs that you see in the surrounding, that are much higher resolution images. But if you want to cover a larger area in a shorter um, time, then beside the aeroplanes photogrammetry, you can also use satellite images, and these satellite images are also available online through Google Maps, Bing Maps, and so many other websites like OpenStreetMap as well. So all these images can be taken by our own devices, our own satellites, but can also be uh, taken from available sources online. We also discussed the coordinate system commonly used for locating any point on the surface of planet Earth. And uh, the system that we commonly use is the latitude and longitude system, which is based on angles. The angles are measured by standing in the center of the uh, planet Earth. So you feel yourself to be standing in the center of the planet Earth and start seeing a point above or below your level of sight. That angle starts from 0 all the way through 90 upward, and these are called latitudes. So any point on the North Pole will be at 90 degrees at latitude, and any point on equator will be at 0 degrees on the latitude. Um, and similarly, you can go towards South Pole by taking negative angles downward, and the South Pole will be at minus 90 degrees. So this means the latitudes, which can be analogous to y-axis on Cartesian coordinate system, varies from minus 90 to plus 90. So we can literally locate any point vertically on planet Earth using latitudes. The horizontal lines seen on this figure here are representing latitudes at different degrees. So subdividing these degrees into minutes and then seconds further into further decimal places can locate a uh, pinpoint location on the surface of the planet Earth. In order to get the location on the x-axis, we use longitude, and longitudes have to start from a 0 degree as well. So because the system was developed by British, they have considered their country as a 0 degree location. So Greenwich uh, in London, a location in London, is considered to be at 0 degrees, and any angle taken from Greenwich towards east is a positive angle, and if you keep measuring it from 0 degrees all the way to 180 degrees, you come back to the same vertical circle which represents 0 degrees. So 0 and 180 degrees are actually a same circle, but a semicircle at 0 degrees passes over Greenwich, while the other at 180 degrees passes totally on the opposite side. And these angles can also be taken as negative, and in negative, which it will mean to take an angle towards west. So if you want to locate anything on x-axis in the west direction, you start measuring from 0 degrees negatively. So all the way from 0 to minus 180 degrees, uh, y- you have all the angles that can be used to represent any point on the surface of the earth in x direction. So all these vertical lines represents certain uh, angle at in x-axis direction, and uh, as usual we can subdivide it into these degrees into minutes and seconds, and then these seconds can further be divided into uh, further decimal places to again get a pinpoint location along x-axis. So all these angles are seen from the center of the earth. So from the center of the earth, you can see outside towards any point on the surface, and then you can locate it along x-axis on the longitude and along y-axis uh, using latitudes. So now you can locate any point on the surface of the earth. Any question up till now?
No, sir. Thank you.
No, sir.
Excellent. So this system of latitude and longitude is um, um, famously established by European Petroleum and um, European Petroleum Survey Group, which is in short known as EPSG, and they developed several other systems as well, but uh, this was usually for petroleum extraction and exploration. But now this system is commonly used for so many other purposes. For example, in GPS, and mainly GPS uses these systems. So if you turn on your mobile phone and turn on your GPS location, it will give you your position where you are standing in the units of latitude and longitude, and that is the European Petroleum Survey group format of your location. There are other methods also used to locate yourself on planet Earth for different purposes, and there are actually different projections of planet Earth, and we talked about that in the last lecture, that a projection can be a globular projection like this one, which gives a projection of the planet Earth on the globe outside it. So you consider another larger sphere outside planet Earth and project every point from it, from the surface of the Earth, perpendicular to that globe outward. Once you do that, you see that globe, it will look like this. This gives you a realistic picture of the planet Earth, but then the farther parts will appear smaller and closer parts will appear larger, like ear is larger and uh, the nose is relatively smaller than uh, appearing smaller than how ear is, but actually it is actually far away from us. That's why it appears that way. Now if we project it on a orthographic format, and which will be taking a piece of paper, rolling it in the form of a cylinder, and let me draw one for you. So that cylinder will be something like this. So, and then projecting every point on the surface of the Earth perpendicular to the cylinder inside of the cylindrical surface. Then what we see is the orthographic projection, and you will see that everything is near the equator is exaggerated, and anything on near the North Pole is also plumbed up and stretched. You can compare it with the neck here. Here, neck is of the normal size, but you can see the neck is stretched at the south and north pole as well. So everything gets stretched on this type of projection. And in the stereographic projection, you can see that everything on the equators roughly remains the same size as of reality, but then, sorry, at the poles roughly remains at the same size, but then the equator get shrink because of this type of projection. This is uh, the uh, again another type of spherical projection, but the most commonly used online on the websites and in the books that we see is the projection which is called Mercator projection, which looks like a piece of paper like this. And here you can see that North Pole and South Pole are so much stretched and exaggerated that they become very, very wide. So even North Pole is just a point. You can see this point here, but it is stretched to the full width of the equator. So this was the width of the equator, which remained as it is, but the North Pole, which is just a point, not a line, gets stretched a lot. But this is a most common way of seeing the maps of planet Earth online. So if you go to Google Map, you will see a map like this. If you go to if you go to Google Earth software, you will see a projection like this, a globular projection. But in Google Maps online, you will see such type of projection. So OpenStreetMap is a free source of maps, unlike Google Maps and other proprietary software. And they also give you the same type of marketer projection. So um, the uh, maps that we will be using for civil engineering purposes will also be of similar type, but mostly when you go to a site to get a point and you use a GPS device to get a location from your mobile phone or from a GPS device, that comes with uh, this type of a system, which is latitude and longitude form. So here on this map, you get the location by meters or feet as a distance. So your origin is here on the top. So from the top, you say, or it can also be at the bottom. It depends upon what software you're using. But it start measuring the distance uh, from in X direction called easting, because we go from west towards east, and from down when we go upward it is called northing. So any point, just like a Cartesian coordinate system, is taken as in on x-axis and y-axis. Instead of that, it is taken as on easting axis and northing axis. So like a point here on Cartesian coordinate system, if it is at 10 meters on x-axis and 50 meters on y-axis, we will be saying it is 10 meters east and 50 meters north. Another big difference from Cartesian coordinate system is that here uh, in Mercator system, the grid is squarish near the equator, but it becomes extended rectangles towards the north and the south. So here, if you think of this image of planet Earth, the North Pole is shown as a stretched point totally on the top, and these last three grid lines on the north are shown, but here in this figure, the last three on the south are not shown. So there is a south pole at the bottom here as well, but they haven't shown it here. So otherwise, that will be a very wide bottom part of the marker system as well. Any question about these systems?
No, sir.
Right.
Okay.
The vertical distances in latitude are also known as the datums, and here is mentioned here the datums. So if anyone asks you on the Cartesian coordinate system, what is the value on y-axis? Here in this system, instead of saying the word y-axis, people will be asking, what is the datum of your location? So you will be saying, I'm 30 degrees north, or I'm 30 degrees south. So that is the value of the datum in degrees. And the unit will be called, the unit will be degrees, and it's is generally known as latitude. The x-axis location is commonly known as meridian. So Greenwich is at 0 degrees meridian. It is also known as prime meridian, and even time starts from prime meridian, which is also known as Greenwich Mean Time (GMT). So when the sun rays hit this line at Greenwich, we say zero time has started, and once a full rotation of planet Earth occurs, and from light the Greenwich turns into dark, and then sun rises again at Greenwich, we say 24 hours have passed. So once the sun rises at Greenwich at 0 GMT or Greenwich Mean Time, in Pakistan already sun has risen 5 hours ago. So that is why we say that Pakistan is at 5 plus Greenwich Mean Time, while anything towards west will be at negative time zone, or that zone will have a negative because the sun hasn't risen there yet while it is rising in England. So this is a system which on x-axis, which is commonly also used for time as well as location in degrees, uh, time in hours, and the uh, angles and degrees, and that is why the 24 hours are divided into every hour is divided into 60 minutes and then 60 seconds, and we use minutes and seconds uh, for uh, time as well because of these degrees. So time in hours is divided into minutes and seconds because actually angles are here are involved here, and angles are in minutes and seconds. Um, so that is the reason we use the same unit for time as minutes and seconds that were used for angles at first, which were degrees and minutes. Sorry, degrees, minutes, and seconds. So let's continue with this topic. And
सर 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 ये इस लेटीट्यूड और लॉन्गिट्यूड के सिस्टम से हम एरिया को कैसे लोकेट करेंगे? मतलब हम पॉइंट को लोकेट कर लेते हैं, लेकिन एरिया तो पॉइंट्स से बाउंडेड होता है, तो उसको फिर कैसे लोकेट करेंगे?
uh, yes, anyone in the class who don't understand Urdu language?
I understand it, sir.
Yes, Jafar, thank you for letting me know. Your colleague just asked a question that we can find a location or a point on the surface of the Earth using latitude and longitude, but we cannot. How we can actually find the area on the surface of the Earth? I told you in the last lecture as well, and it's a very important question, that the reason we have squares in the universal marketer projection or UMP or UMT um, is uh, that we have squares in near the equator and rectangles towards the north is actually to find out exact areas. So if you notice here, if area of this one small square is 1 square kilometer, for example, and in the north this square is stretched to this size. So the area of this elongated rectangle is also 1 square kilometer. So we use these grid lines to find out areas. Uh, Here the area is taken as 1 square kilometer, and here this small square area is also taken as one square kilometer on planet Earth. Same applies to all these grid lines. So here you can see a big square is in the center. Its area is also 1 square kilometer, and a trapezoidal type of a shape near the south pole or the north pole here represents the same area. And same goes for this. You can see even there are triangles near the south pole and near the north pole here, and these triangular shaped areas have the same area as this very large uh, curved curved edged square and near the outer boundaries of the circle here, and same goes for this side as well. So these grid lines are curved and irregularly spaced just because we these figures now represent wrong areas, and now we can get correct areas using these grid lines. Does that answer your question, my friend?
Yes, sir. Sir, that's good. But I asked that suppose we have to look at Pakistan boundaries, so it's almost irregular. So how can we utilize the squares and rectangles to boundary relation?
Excellent. That is a concept that you're talking about, and it is mentioned as grids. So there's a concept of how to draw these grid lines. Then we can use these grid lines to find out areas and also locations on the planet Earth. So this is a separate topic where we will learn how to actually draw these grid lines. And to understand that, we need to know some more topics like the World Geological Survey 1984, World Geodetic Survey 1984, and so many other similar knowledge. We need to know that in order to understand the answer of your question. So shall we continue?
Yes, sir. Thank you, sir.
Okay, thank you. So, yes, Mr. Anis, you cannot hear me well?
Yes, sir. Volume of
Your voice is not clear.
Let me check my microphone once again.
सर क्लियर है आवाज?
अच्छा, अनीस साहब आपकी तरफ इशू है, आप काइंडली अपने स्पीकर को या वॉल्यूम को सेट करें, हेडफोन को सेट करें। बाकी स्टूडेंट्स को आवाज ठीक आ रही है। सो लेट मी कंटिन्यू। Right. The planet Earth is typically considered as elliptical in shape, but in reality, it is a very rough shaped object. You can see there are hills and trenches in different locations. The elliptical shape of taken from the center of the geometric, or sorry, the center of the mass of planet Earth. If we draw that ellipse, that is green in color in here, will cover the south part of the Pakistan of the world very easily, of this blue boundary, which is the realistic planet Earth, but just exaggerated in more elliptical shape. But this ellipse drawn from the center of the mass of planet Earth will not cover the north part, it will not overlap the north part of planet Earth very well. This is a similar type of a survey uh, or a method used to locate a point on the surface of the Earth, which was done long ago by Clark in 1866. So this is a similar type of an ellipse. Now, what do we mean by that is ellipse has an equation, which is something like x square over a square plus y square over b square is equal to 1. So in this equation, we can locate a point uh, at any x and y location. And of course, it's a three-dimensional ellipsoid. So it will have x square over a square plus y square over b square plus z square over c square is equal to 1. So in that case, we can locate uh, any point on a three-dimensional ellipsoid surface, but that may miss many points or give wrong locations using this equation. So this equation is the surface of the ellipsoid, and somewhere it gives points which are outside planet Earth, and sometimes it gives us points which are inside the planet Earth, not on the surface. So Clark 1866 method of locating a point using XYZ system was very faulty. That was improved further by another group of people, uh, and that was recorded in history as GRS ellipsoid, GRS 1980, and that you can see is a blue shaped object outside planet Earth here, which is very close to the surface of planet Earth, while actual planet Earth is called geoid because its shape is not ellipsoid. So we give a new name to it, which is called geoid, and an exaggerated view of geoid is shown here. The highest point that we see on land is the Mount Everest on planet Earth. The uh, farthest point from the center of Earth is near the equator in a place called Chimborazo. And similarly, there are lowest points on the land like Dead Sea and then the Mariana Trench underwater in uh, is the deepest point. So there are deepest and highest and farthest point on planet Earth, which makes it a geoid shape like this, which is an irregular shape. But we like to fit equation to this planet Earth, so that it roughly gives a location on planet Earth, and ellipsoid equations serves that purpose. And now we have a much better ellipsoid, which is planned by World Geodetic System 1984, which is also commonly known as EPSG, or European Petroleum Survey um, group, European Petroleum Survey Group. There are several types of um, similar systems used by similar systems like used by EPSG. So EPSG has been now not only used for petroleum purposes, but also exploration purposes, but also for online maps and globes and so many other projections. The common projection that we see on paper maps, on websites like Google Earth and Google Maps, is EPSG 4326. This means, as civil engineers, because we will be commonly using uh, this type of map like Google Maps and OpenStreetMaps sourced from the websites, because we will be using those maps, we will be using EPSG 4326 projections all the time. But then if there are some other type of maps, like a three-dimensional map of planet Earth, then the projection will be very different. So let me verify this information once again. Yes, I was not right in saying that. Let me revise this. So if you are working on the units of latitudes and longitudes, like we use in our mobile phone GPS system, then EPSG 4326 is used for that. This means our mobile phone use EPSG 4326 projection. Why? Because it works in latitude and longitude. But if we are working on northing and easting, then another system of projection is used, and that the name of a technical name for that projection for latitude and longitude is uh, EPSG 3857 instead, not 4326, but 3857, which is also known as web marketer projection. And it gives us location on the surface of the planet Earth in the units of northing and easting, and the projections shown on the Google map and the OpenStreetMap are EPSG 3857, but in your mobile phones it is 4326. So just like we have to convert projections from Cartesian coordinate system into polar coordinate system. So in Cartesian coordinate system we have x and y in feet or meters, but in polar coordinate system we have a distance from the origin and an angle of that vector. So it's in r theta format. So we can convert r theta into xy by taking sine and cosine, and vice versa as well. Just like that, you need to convert your latitude and longitude, which are in EPSG 4326 system, into northing and easting, which is EPSG 3857 system. So we can also do these conversions, and if we don't do these conversions and we use the data from one map on to show something on the other map, then we are seeing things wrongly. It is just like this, that you found a point on the outer sphere here, which was on WGS 84, and you draw that point on the map, which is drawn on this red circle. So, for example, if you go find a point here, which is at let's say 10 degrees east and 50 degrees north, and you locate that on here, it will give you a very different location compared to this one. So these need to be converted from one coordinate system to the other. So a 10 degrees east and 50 degrees north on WGS 84 may be 5 degrees east and 7 degrees north on Clark 1866. So there are formulas to convert them, and there are software that can do that easily for us. So similarly, if you use your GPS device, which uses EPSG 4326 to find your location, and then you want to find your location, you want to locate that on a Google map, which is actually based on EPSG 3857. So you need to convert 4326 into 3857, and software like QGIS or Quantum GIS and ArcGIS have the capability to do that. They have the formulas known. You can go online and look at these formulas as well, but you don't need to go in that detail because the software uses those formulas to do these conversions for you automatically. So commonly, it is known as World Geodetic System 1984 data, and we will be using this WGS 84, which is also known as EPSG 4326 for our future maps. That whenever we'll draw them, we'll use them. And otherwise, if they are downloaded maps with EPSG 3857, we will convert them into EPSG 4326 because our points that we get from our GPS devices in our mobile phones are on 4326 system. They're trying to improve the quality of these with the passage of time. As you can see, 1866 ellipsoid was very wrong. They improved it to a very good one in GRS 1980, then much better in WGS 84, and now there is a modern one which is WMM, which is based on the magnetic nature of planet Earth, WMM 2020, which was supposed to be released this year, last year actually, and they have now a better representation for other purposes. But for our application as civil engineers, WGS 84 is very good, and we are not always working for the whole world. We are just working on a small area on planet Earth, which is Pakistan. So for Pakistan, WGS 1984 is well suited and enough. Any question up till now?
No, sir.
Okay, thank you. Let's move on with this. So let's see what are different types of maps. Here we see two major types of maps. One is called a general map, which is actually a photograph of planet Earth, and it has some international boundaries being drawn on it, and some major capitals and cities have been marked as points, and their names have been written, so as well the names of the countries, and the colors here show the nature of the land. And for example, white color shows snowy or glacier areas. The brown color shows rocky or sandy or dry area. The green color shows the vegetated land as well. And blue color is representing the water. So generally how human beings see things, how we perceive things, those colors are used to represent different locations on planet Earth. So these type of maps are called general maps. They give us general information as visible to us from satellite, from aeroplanes, or on the ground as well. Other types of maps the civil engineers are usually involved with are called thematic maps. So they use a theme to color theme to represent other type of data that we cannot see, but we can observe using some methods. So these are the things in general maps that we can see using cameras installed on devices like satellites, drones, or from ground. But here in different themes, we cannot see but observe these things or phenomena or processes, and we can draw them just like we have drawn this one with colors. We use a different set of colors here to represent something else. For example, in this particular thematic map, wherever there is a population uh, which is less than one, so there's almost no one living in that place, that is white in color. And as the population increases, a low population from 1 to 2 person per square kilometer is represented in yellow color. The as we increase the population, the red color represents 60 to 120 uh, uh, persons living in a square kilometer area, and a black color is showing a population of more than 1,000 people living in a square kilometer area. So once we divide the whole country into small areas, and then we use these colors, we go to the site and we observe the population, we count them like we commonly do in census. And once we have the count within these political boundaries, and we color the whole area accordingly, we see such map. So we can, once we have drawn this thematic map, this is the population density map of Pakistan. Now, looking at this map, we can take so many decisions and we can get so many ideas. For example, the western part of the Balochistan is least populated. Most part of the Pakistan surrounding the Indus River is very densely populated, and Peshawar is also very populated and densely, not very much densely, but then moderately populated city or a district, because these are district boundaries. Similarly, another thematic map can be an earthquake zone map as shown here. So in here you can see um, the different areas where we have higher possible chances of severe damage causing earthquakes that can appear are red in color, while earthquakes, if they cannot do much damage or minor damage only in certain areas, then they are green in color, and then other colors representing uh, moderate and other minor or moderate type of damages that an earthquake can cause. So we can create earthquake zone maps like this. So red areas representing zone 4, for example, and green area zone 1, blue zone 2, and then orange color as zone 3. And these, now we can easily see that Peshawar is in zone 2, while Quetta and Islamabad areas and Muzaffarabad areas and Run of Kutch areas, Gwadar areas are in zone 4 according to this map. But because every year earthquakes come and the fault line increases in length and changes the position as well, so these maps need to be revised after every earthquake. Any question up till now?
No, sir.
Okay, thank you.
No, sir.
Thank you.
No, sir, no question.
So next we are going to talk about a concept of vector and raster. We lightly talked about it in the last lecture. First of all, in the bottom right here, what we see is a real image of a, a part of planet Earth. This is actually a Google Earth image from an aeroplane taken for of UET Peshawar. Here we have civil engineering department. Here we have civil lawn, and here we have office building, mechanical department, earthquake center, and so on. So this photograph is a real image as what we see, and it has frozen the information for that time when we took this photograph. But then with the passage of time, everything changes. The shadows change their location. The traffic, if we trying to note that, its density increases and decreases with the passage of time. Trees being cut and new vegetation grows, grass dries, and so many other phenomena keep occurring. But then this particular image has frozen the status of that particular time, and we have that information available. We can see the roads, how they're linked together, the building sizes. So if you go to the civil department building now and find out its width, so you will have an idea that how much this distance is. Then using that scale, you can find out distance or the length of this road, width of this road number 2, and so many other dimensions can then be taken by using just one reference. So a reference is very important for such type of photographs to get an idea of sizes and distances on such real images. But this image is not understandable by a computer directly, and we can not ask computer to give us area of this industrial block, a building or civil department building. What is the covered area of this building? If you ask the computer to find it for this from this photograph, it cannot do that. In order to achieve that capability, we need to convert this photograph into a raster or a vector image. Now, this image already is known as a raster image, because if we zoom on it a lot, for example, considering a real image here of the real world, which has a river and a building and some trees here, its photograph will be something like this. If you zoom on that photograph a lot, you will see that it will look like pixelated, something like this. You will see these pixels, and the blue color here will show a river to us. The green color will show some dense vegetation, and some light green color will show us some open green patches, and some other colors will show us some habitats like houses, etc. And uh, any other color may show any other feature, roads, and so many other things on this raster image. Now, these colors can be identified, and then they can be uh, marked as river, forest, or buildings automatically by a computer. So actually, if you ask a computer to use any gray color and mark that as a building, then it can start identifying some things with some error. So in order to reduce that error, what we do is we use our computer and a software like AutoCAD or maybe QGIS to draw polygons to represent these things. So for example, for this actual river on this raster image, we draw a polyline that represent the center line of a river, and then we name that polyline as river. So if we similarly, we draw a polygon surrounding the dense forest like this, using the multiple points and some other green patches, and a point. If we use a point to represent a house, then a line, a polygon, and a point can be used to represent anything on the surface of the earth. And if you want to now find out the area of this dense forest, it is hard to find it from a real on a real ground, but in these pixels we'll get some rough idea. But if we find the area of this polygon, it will be much accurate. So that is why converting reality into a raster by taking its photograph, and then converting a raster image into its vector form manually or by using a computer software, will give us an opportunity to use this information for our calculation purpose. So now, if we ask computer to find the length of the river here, it will not be possible here, or it will be a very tedious job to do using computer. A computer gave us a rough idea of the length of the river from this raster image, but not accurately. But if you ask a computer using this vector, it will easily find out the length of these vectors, and it will tell us the length of the river very easily and very quickly. So that is why we use satellite images or photogrammetric images from drones to take raster images and then convert that reality into raster and then convert it into a vector form for our purposes. So the vector form of same civil department building and other surrounding buildings in this raster image are shown above here on the top right, and this polygon is now representing civil department building. This one can be used to find out the area of the earthquake center, and the area of this polygon can quickly tell us the area of the civil lawn. Any question about vector, raster, and real?
No, sir.
Fine. So what is raster?
Thank you,
Raster
sir.
is a photograph. What is vector? It's a polygon line or a point drawn over that photograph, and real is what we see from our eyes as a reality. Now, as mentioned earlier, that vectors are very important for us as civil engineers, and they help us quite a lot in taking certain decisions. So, the one of the most basic type of a vector is called a point, and a point can be represented by its location as x, y, and z. And if you are using the EPSG 4326, this will be uh, the x-axis will be longitude, y-axis will be latitude, and z-axis will be elevation above sea level. Every vector element like this point has certain attributes, and at least it have these three attributes, but it can have more attributes as well. The three important attributes are its ID, its name, and description. For example, 2 points are shown here. One is blue and other is purple in color. So blue point and purple seems to be two different points, but we cannot understand what are these. But we can understand that by knowing their attributes. So for example, uh, blue point has an ID 1 and purple has ID 2. So now we can differentiate them by their ID, that this point is 2 ID and this is ID 1. So we don't need to represent them by color anymore. Then blue has a name. So ID 1 has a name, and that is a tree. And purple one is a light post. एक बिजली का खंभा कह लें. And then tree has certain description as well, that it is outside our classroom, and the light post is at the entrance of the civil department building or school entrance. So now with these three information, we know quite a lot about it, this point, and quite a lot about this point as well, and we can now use this information for taking certain decisions, and this is called GIS. Now we have a geography, we have a distance between them. What do you mean by that? We have a map now, a very simple map with just 2 points shown on it geographically, and we have an information about these points, that one point is a tree, other is a light post. We have further information that the point is outside a classroom and the other point is at the entrance gate of a civil department or school building. And another information is they are differentiated by their IDs. The one is an ID 1 and other is ID 2, so we can now call them by their IDs. And this is a simple geographical map, so a basic geographic information system. Sometimes we need to show certain details that can be well represented by a polyline instead of a point, and they're shown here on the right side. And here again we have two different features shown here. One feature is um, a polyline created by joining blue points, and the other one is purple points. And of course, it should have at least 3 attributes, but it can have many other. You can add more attributes to it too. But currently, ID, name, and description are important and mentioned as below. For example, number 1 is a footpath, and ID number 2 is also a footpath, but their names have been changed as footpath 1 and footpath 2. The blue footpath or ID1 footpath goes from classroom to a playground, while the purple colored footpath or footpath with ID number 2 goes or connects school's main gate to the dining hall, for example, or Akhtar Naim Hall in our main building. So these 3 things tells quite a lot about these polylines. Without these attributes, we were not able to use this uh, map at all. But now with this map, we have this information all together. So we call it a GIS information on because of that. Another description here can be beside description, we can have many other uh, attributes as well. For example, another attribute we can add on it, and we can, as a civil engineer, we can have an attribute of construction status. So for example, the footpath in blue color already exists. So we can have a construction status of built. And if the footpath in purple color has not been built yet, so we can have a construction status as planned. So we have a comma here, we can have a comma here, and we can write build. And after here, we have a comma here, we can write planned. And here, after description, we can have a comma and say construction status. So we can have so many attributes, and they can help us in taking certain decisions and do our planning accordingly through this GIS maps. So there are certain other features that cannot be represented by points and polylines. So for that, we draw polygons. So for example, again, a polygon created by joining blue colored points and another polygon by joining purple colored points, but we don't know what are these things beside unless or until we know the attributes of these polygons. So these 2 polygons have their IDs, names, and descriptions, and we can have so many other attributes as well. But here, ID1 is blue and ID2 is purple, and ID1 is the boundary of the whole school of civil engineering, and ID2 is the boundary of a sports ground or civil lawn behind our building, for example. And description tells that um, this the blue polygon is the fence line or boundary line, boundary wall of our school, while purple boundary is as a description that this is a place where we play football or soccer. So this is how we can use the information table or attribute table along with the map to get an information connected to the map. And once any information is connected to the map, we call it a GIS system. And if you're using a laptop or a mobile phone to see or observe this map, and then we have a complete GIS system ready. Any question up till now?
No, sir.
Okay, thank you. Now georeferencing. So we have just drawn 3 maps a while ago. One is a map of points, other was a map of polylines, other was a map of polygons, and before that another map was here which had all these 3 features, for 2 polygons, 1 point, and 1 polyline for a river. So once we have drawn all these maps using vectors, we have very good GIS information. So here in yellow color we can see a similar set of polygons are drawn for a state in North America. It's And here we have so much information can be connected to the attribute in the attribute table of all these polygons. There are almost no points and lines here, but only polygons are here, and every polygon has its own attribute set. So this information is on this map, but the problem is we don't know where exactly it is on planet Earth. So here this is showing that where this actually all set of polygons actually lie on planet Earth. So what we do is we know that now we have systems of WGS 84 or EPSG 4326 that represents coordinates on planet Earth. So if to any point on this map we assign those coordinates on planet Earth from latitude, longitude, from your GPS or anything, if to any point on this map, if you represent that with those coordinates, then from that we can measure distances anywhere using a scale drawn on this map as well. And of course, we have to orient this properly. So if in reality, this is the direction of the north upward. So here on this map, we also draw the upward as well to orient this map properly. Without the north, we don't know how to place this on planet Earth. But with the north shown, we now know how to place it there. So with a point on the real Earth, knowing its coordinates, if you represent any point on our map with those known coordinates, world coordinates, and then show the orientation by drawing a north symbol, and then we don't know how big or small this is, so show a scale on it too, that how big it is in reality in kilometers, for example, then this map is said to be georeferenced. This map is now referenced with the planet Earth, with the geo. So georeferencing is the process of assigning real world coordinates to each pixel of the raster image or the vector image even. So many times these coordinates are obtained by going to the field and doing the field survey, or by collecting coordinates with GPS device uh, of one or two identifiable features on the map or on the image. So for example, here uh, we can easily identify the civil department building. Even this corner of the civil department building is perfectly identified on this photograph. If you go there in reality, turn on your mobile phone GPS device, get your coordinates and write them on here, and go to this corner of this road as well, which is easily identifiable on the ground there. Turn on your GPS and get the coordinates from there as well. So these 2 points are now known. You just put them on the map, then these are enough. You don't need a scale on this map. You don't need the north as well, because using these 2 points, you can easily guess where is the north, where is the x-axis, where is the y-axis, or northing or easting, and what is the distance between them, because you have 2 reference points. So only 1 point will require to have a north symbol and scale drawn, but with 2 or more points known, you don't even need north and scale. That can easily be calculated using these coordinates. So this is what is called georeferencing. So whenever we will be drawing our maps, we will georeference that map with 2 or more points, or with 1 point and north and scale of that map. Then we'll say we have done the georeferencing, and it is very important because it will be used to locate other places we haven't visited, but we have drawn them on the map, but we haven't visited them yet. We can locate them, we can get so much information, their distance, their areas from the map, unless or until it is georeferenced. Any question about georeferencing?
No, sir.
Okay. The next concept is digitization. If you remember a while ago, we were saying that we have a photograph of planet Earth or a part of planet Earth, like in this photograph here. We have the photograph of civil department area and surroundings, which we said is a raster image. Now, in order to convert this into a vector form here, we had to draw polylines on it in a software. But first of all, we need to import this photograph into a software. Once we import it, we don't know where is it located, so we georeference it in the software. So in AutoCAD or in QGIS software, after importing this image, we georeference it. For example, we can say that this point in the civil department building here in this corner is at this much latitude and longitude, and this corner here on the road is at this much latitude and longitude. So now this photograph is georeferenced, and now all distances can be real distances on this photograph. Using the polyline or polygon or point tools in AutoCAD or in QGIS software or in any other GIS software where you have georeferenced this image, now you will start drawing polygons on the surroundings. Now automatically all other points you will draw will get coordinates automatically. You don't need their coordinates because this map is georeferenced. It knows all distances and all lengths and all locations. So wherever you will click, now GIS software know the coordinates because this is a georeferenced image. Do you understand what I'm saying?
No, sir.
Yes,
Yes,
sir.
sir. Yes.
Yes.
Good. So once
सर एक बार रिपीट कर दो.
G, um, if we have a photograph of a civil department area like this, and if I draw a point on it without georeferencing, maybe a point of here on the tree in the civil lawn, I don't know where it is, and the computer software also, if I open it in MS Paint or Paintbrush software, it doesn't know where this is located. But if I tell that this point here is at um, at a latitude and longitude of 10 degrees and 70 degrees east and north respectively, and this point is at 20 degrees and 75 degrees in east and north respectively, then with the reference of these 2 points, wherever we move our mouse pointer, for example here, we can know that this point is, then if this was at 10 degrees east, this is also at 10 degrees east, but it has moved 5 degrees towards north as well. So it is, this point is if this was at 10 degrees east and 70 degrees north, then this point is 75 degrees north, and it remained at 10 degrees east. So at x-axis, we haven't moved, while at y-axis, we have moved 5 degrees. So we just add 5 extra degrees in the north direction. So once this map is, or this photograph is georeferenced, every other point location is very easy to locate. Is that clear?
Yes, sir. Thank you.
So now if we click on this tree, we know the coordinates of this tree without
Yes, sir.
using a GPS device. And if I use AutoCAD or a GIS software like QGIS to draw a polygon on civil department classroom building, then that polygon has 4 points, and the location of these 4 points is already known to the software because this image is georeferenced. So if we draw it manually, or if we ask software itself that wherever we have gray color object, draw boundaries surrounding it automatically, then it will draw a polygon automatically around it for us as well. We don't need to do that, but we can do it manually as well. This process of drawing these boundaries manually or automatically is called digitization. For example, here in this small short video, this person is trying to draw a polygon, uh, 2 different polygons, one this blue square, and now it will draw another rotated irregular on a rectangle or polygon at an angle. So this is hand-drawn polygon. So this is a process of digitization. We can also do digitization of not only a photograph, but of a scanned image or a scanned map as well from a hard copy. For example, if you go to a property dealer of your area, that person have drawn a map of your area by hand and named those plots, referenced those plots differently. So if you scan that photograph and you draw polygons on it, then you can say that you have digitized that map. Now computer can understand and you can take certain decisions and certain information as output from those maps using GIS software. So another thing is another very important concept is geocoding. We lightly talked about it in the last lecture as well. You can understand coding as coordinates, and you can reference geo as a real address, for example. So geocoding is actually converting a real address, human understandable address, into coded coordinates, a computer understandable address. So computer cannot understand if you ask computer to take you to civil department building, which is here. It cannot understand that. But if you say that take me to 31 degrees east and 72 degrees north, it will take you to that point on spot very quickly and very easily. So what we have is we have a table of a system where we have all these coordinates related to some addresses. So an address which is human understandable, maybe in Urdu like this, or maybe in English like this. So if you tell this statement to anyone, human beings can understand them very easily among each other. But computer and human cannot talk to each other with this address. So in order to create that communication between computer and human, we have a system of geocoding. So our addresses, we have a table of this address. In that table, we have written address in one column and it's northing and easting in other columns. So whenever we say take me to civil department, civil engineering department building, computer go to that table and find out what are the corresponding northing and easting or latitude and longitude for this address and take us to that on the map. This is how Google Maps work. Oppositely, if you don't know uh, what is the address of this point, for example, so you can ask computer that at this coordinate, what is the address? So you just click here, and because this map is georeferenced, it knows where you have clicked. So it takes these coordinates, go to that table again, and corresponding to those latitude and longitude, find the address and tell you on the screen that the address of this location is Civil Engineering Department building, for example. So that is called reverse geocoding. So in order to communicate the location between among us as human beings, we just simply talk about addresses, and computer uses coordinates to communicate locations with other computer devices. But when we need to communicate addresses between computer and human beings, we need geocoding for that purpose to tell computer what we are talking about. We do geocoding. And if we want to understand what computer is telling us, what location computer is telling us, we ask it to reverse geocode it for us. So there are several databases available, and in coming lecture, we will be discussing about geocoding in detail. So now I'll also give you a slight introduction of QGIS software and we'll conclude today's lecture. So the software that we are going to use for in this course for GIS purpose is called QGIS. So you simply go to um, your browser and search for QGIS. You will find QGIS.org website. You can directly go to the download page from here, or you can go to the main website and find it, other details, and you can browse to the download page from there as well. But I directly go to the download page from here at the moment, or maybe go to the actual website. So here's the main website, and you'll see on the main page it will have a download now for your based on your operating system. So if you click on that, you can, if you're using Mac, Linux, or Android phone, even you can install it on your Android phone as well, or your Android tablet. Now you can download the 64-bit software from this link. You can download it on 32-bit Windows from here. You can download only a limited QGIS standalone software in 64 or 32-bit latest version from here as well. But I found them to be relatively unstable, and the most stable one is the 32-bit one that you can download from the network installer. It takes some time to install because it configures it to your computer, and if your computer has some limitations, it handles those limitations as well. But then if you download the standalone installer from here or from here, it will not do that processing and it may crash for you. So if you don't want to get yourself in that trouble, even if your computer is a 64-bit, has 64-bit capabilities, I will advise, if you want to take if you don't want to take any risk, better download a 32-bit version of QGIS software, and from this link install it. It will take some time compared to this installation, which is very fast, but it has risky issues in the way that it may not recognize certain features of your computer, but here it will configure it as it is designed for your computer. So you may download this link, from this link, the software. Once downloaded, it will uh, you can install it, and once installed, uh, on your computer you can search for QGIS, which is installed. So I installed 3.12 version. 3.16 is now available. Even if you install an older version, it will work fine as well. So you simply click on the QGIS 3 app. Once you click it, it will take a certain time. You can install 3.16 version as well, but for me, I'm running 3.12 version. So once you run it, it will show you a screen like this. It will have a menu bar at the top and the main toolbar at the second from the top, and some other sub toolbars there as well. On the left here, you will have a browser which has a link not only to your computer but to other computers around the world, which provide you free or paid maps of the world as well. There are some other tabs here as well that I have installed, but let me close this digitizing tab now. The second important window you need to open here is for the layers on the right here. If it is not visible, you can always right click on the menu here, anywhere on the toolbars, and you can select the panels that you want to show. So currently the browser panel here is checked, the layers panel here is also checked, visible, and processing toolbox panel is also checked, which is shown here on the left. If any extra toolbar is required, you can right click and select the toolbars that you want to be visible. You can also turn off the toolbars if they're not required. So if any toolbar is required but it's not visible, you can always right click on the any toolbar, and you can not only bring these toolbars but also the panels, missing panels as well. Um, Processing toolbar is the common one that we'll be using, and browsers are always required, and layers are also always required here. So the maps, the way the maps are provided for the planet Earth, the most common type of file that we use to save and to share maps among ourselves is called shapefile. Just like in Microsoft Word, you have doc file or docx files that we share among each other to share documents that we have written. If anyone asks you to share a map with you, you will prefer it to be shared as shapefile or SHP file. Now, SHP file or a shapefile is invented by ISRI, which is a department in international organization that standardize mapping techniques around the world. And ISRI is provided us with the shapefile format. So, for example, if you are interested in a shapefile for Pakistan, what you will do is you will go on your browser and you simply search Pakistan shapefile. So this is a better way of searching for maps that can be used for decision making or GIS purpose in your computer software. This is one of the better way of searching for such maps. So here, this is a website which is United Nations humanitarian coordination website, and this is a data website for data.humdata.org. So the United Nations OCHU, which is the organization of coordination for the humanitarian reasons. Their organization provide free data around the world, and this is one of the link for that purpose, and it provides us shape files for Pakistan administrative boundaries, so we can download these files from there. If you click on this link, by the way, if I go back here, there are several other sources of shape files that can be downloaded for Pakistan and other countries as well, and even the whole world. But for now, let me click on the United Nations source. So here we have subnational administrative boundaries. If you see this data is available in Excel form, in PDF form, in G database form, in zipped format, and here we have zipped shape files. We also have Google Earth KM zip files, also Microsoft EMF extended meta file format files, and other P code map server, feature server formats as well. So we are currently interested in shape files because they are the polygons, lines, and points stored for GIS purpose in SHP format. So the digitized maps of points, polylines, and polygons, whenever you save them in QGIS or ArcGIS or ISRI or any software, they're saved as shape files. So instead of making a polygon by ourselves, for now, we'll learn that in coming lectures. But for now, let's try to open up the already drawn polygons for Pakistan. So here they have shown that they have a layer or a level on it, which is 0 level, which has Pakistan's administrative boundary as a country. Then layer number 1, ID 1, will have provinces and federal capital territory and other autonomous and disputed territories and federally administrated tribal areas. So notice this is a November 2019 map. So it has not merged areas being nominated there. But now, of course, our latest map will have merged area information there too. The ID number 2 layer will have districts in it, and ID number 3 will have tehsils inside those districts as well. So you can click on this link and download this zip file for free. Once it is downloaded, you can extract this zip file into its folder, and you will see that there are so many files in it. So much so that you will also find out, you will find and see as a PDF in it too. Uh, it has SHP files here, all these. So there are about uh, these 6 SHP files or shape files. Notice we have administrative 0, administrative 1, administrative 2, administrative 3, and in the description it was written that these are tehsil, 2 is districts, 1 are provinces, and 0 is the administrative boundary of Pakistan. Beside that, they also provide us some other administrative information here as well. Whenever you copy, you want to share any map with any friend of yours, not only copy the shape file, but also copy the SPX and DPX file with it too, with the same name. So with the same file name, you will see that there are other DPF file, PRJ file, SPN file, SPX files, XML files. Relevant data to this shape file is available in these files as well. So always copy. So for example, for this ADM3, all these files, let me give you a selection. So here, all these files are ADM3 files of the same name, but beside SHP format, they are XML, SHX, SPX, SBN, PRJ, DPF, and CPG files. So SHP will have polygons in it, but DPF will have attribute tables in it. So this GIS information is missing without DPF, and I'm not going in detail of other files, but you always zip these files and share all these files together. So copying SHP file is not enough. All these files are required together to support this SHP file. So let me now go back to QGIS. And now once it is open, you can even click on this new empty project and start a blank project, or you can click on project menu, click on new, or you can click this icon for new project as well. So once you click it, it will create a blank screen for you here. Here it is now showing, if you see in the right, in the bottom right here, it is EPSG 4326. So it is using the coordinate system, which is WGS 84 already, and this is what we want to work in. So this means it is already the planet Earth here, but nothing has been drawn here yet. You can show a raster image here as well as you can show a vector image here as well. You can see that there are two menu items, one is vector and one is raster here on the top as well. So for now, we have downloaded so many shape files for Pakistan now. Let me open one of them. So in order to load that, you can load it from the browser here. Go to the C drive, and wherever you have downloaded that, you can go to browse and go there. But in the other side, you can go and click on layer. Currently, notice here in the layers, there is no layer yet. But if you go here in the layer and add layer and add vector layer, because we have downloaded vector shape files. Shape files are vector files. JPG file is a raster file or raster image. So for now, we are interested in shape file. So here the source is a file. You can directly select a zip file from here as well, but I don't want all layers to be loaded. Just to demonstrate, I'll click on browse and go to that folder. I could have clicked and selected zip file directly, so it could have opened zip file for me, because it can load a zip zip file as well. But there are so many international formats. Currently, we are loading a shape or SHP file. But notice here, it can also open a map that is stored in Excel format, Microsoft Excel format as well, XLS format. Excel also provides us another type of option to save a file in CSV format as well, which is comma separated value file. Will in coming lectures we'll open those files as well, but for now let me open shape file. So here administrative zero boundary shape file is this, which is just Pakistan boundary. So but now let me open actually the province boundary, which was administrative one. So admin one shape file is actually this one. So I click on this and say open. You'll notice that with the same file name, beside SHP file, there is also a DBF file here. So once you open SHP file, it will automatically open other files and take their data as well. We only need to open shape file only. So I click on open, it is selected, and I say add to it, and then I simply close it. So now you see province divided Pakistan is shown here. I'm sorry for not showing Kashmir here. It's a part of Pakistan because it is downloaded from an international source. They are not showing it, but of course, we must add a polygon of Kashmir here as well. Um, Now you see in layer, we have layers, but all these layers, in this layer, all these polygons have the same color. They're not they're not differentiated yet. If you click on any polygon, it will automatically appear in the center of the screen. For example, Sindh now, if I click on NWFP here, you'll see it will be directly in the center of the screen, and Punjab now exactly in the center of the screen. So if you right click on the layer and click on open attribute table, you will see that beside their ID, which is the first thing here, there is an information of shape, length, shape, area. So area of that polygon is there. The name of the administrative boundary, Punjab, Balochistan, Khyber Pakhtunkhwa, Sindh, the code from Pakistan reference, and so many other attributes are shown here. The country code is PK and country name is Pakistan for all these, because all of them are part of Pakistan. The date when it was made, so it was 30th November 2018, and that is why it has merged areas not shown here as well. So, but now let me we'll talk about all QGIS later. This was enough for the introduction of QGIS, but just to demonstrate one of its capabilities, I simply right click on it, go to properties, and in the symbology, I don't like brown color to be shown as a symbol for all of them. I want these all provinces to be shown in different color. So instead of a single symbol, I select categorized, and in categorized in from the attribute table value, if you remember, if I drop down, these are same attribute table values shown here. If you remember, the administrative one EN was having different names for all these polygons there. So I just select them that differentiate all of them, these categories, by the value in written in these names. And then I use color ramp as random colors here, and I click on classify button here. So now it has classified Balochistan, Federal Capital Territory, KP, Punjab, and Sindh with all these colors. If I want to change any color, I can change that. But otherwise, if I say apply to this, you will see now a layer have several sub layers, and now every province is color coded. But if you don't understand this at the moment, how I did that, no problem. This was just for demonstration purpose and introduction to the software. We are going to discuss all features of QGIS software in detail in coming lectures. And this concludes our today's lecture. Any question or comment for today?
सर वो एंड्रॉइड के लिए
नो
क्यू
सर।
फील्ड जो ऐप है वो भी चलेगी?
आप किसकी बात कर रहे हैं?
क्यू फील्ड ऐप की सर, मैंने QGIS वहाँ पे सर्च किया तो वहाँ पे क्यू फील्ड ऐप आई है एंड्रॉइड के लिए।
आप एंड्रॉइड पे इंस्टॉल करना चाह रहे हैं?
जी सर।
आप वेबसाइट पे जाके उसी तरह QGIS की वेबसाइट पे जाएं और आपने फिर वहां पे जाके आप डाउनलोड पे जब जाएंगे तो वहां से आप अपना ऑपरेटिंग सिस्टम एंड्रॉइड सेलेक्ट करके वहां से इसको डाउनलोड कर लें।
ओके सर।
वेबसाइट से कर लें, ऐप स्टोर से ना करें फिर, ताकि आप ऑन स्पॉट चले जाएं उधर। ठीक है?
एक्सक्यूज मी
ठीक है
सर।
सर।
जी पूछिए।
सर मैंने डाउनलोड किए लेकिन जब इंस्टॉल करे तो यहाँ पे तीन ऑप्शंस आ रहे हैं। एक आ रहा है एक्सप्रेस डेस्कटॉप इंस्टॉल, एक आ रहा है एक्सप्रेस वेब जीआईएस इंस्टॉल और एक आ रहा है एडवांस्ड इंस्टॉल।
अच्छा, आप
सर
इसमें आप डेस्कटॉप कर लें अगर आप इजी करना चाहते हैं। अगर आप एडवांस से भी कर सकते हैं, एडवांस में बस सारे फीचर्स आप सिलेक्ट ना करें, सिर्फ डेस्कटॉप इंस्टॉल कर लें आप फिलहाल।
ठीक है सर।
और कोई क्वेश्चन या कमेंट?
थैंक यू सर।
ठीक है, आफरीन साहब ने लिखा है सर वी हैव नेक्स्ट क्लास एट 11 AM। तो बस अभी आपकी क्लास तो 10 बजे तक होती है ये, तो आप क्या कहना चाह रहे हैं? ये 2 आवर्स की क्लास है आपकी। ओके फाइन, द क्लास इज ओवर, आई विल स्टिल वेट फॉर 5 minutes अगर किसी का कोई क्वेश्चन हो, एंड अदरवाइज लेट मी टेक योर अटेंडेंस फर्स्ट ऑफ ऑल।
एक्सक्यूज मी सर। सर इसको इस सॉफ्टवेयर जो सॉफ्टवेयर आपने बता दिया सर उससे डाउनलोड करें इसको?
जी जी, वही सॉफ्टवेयर हम QGIS इस्तेमाल करेंगे। अगर आप कोई और इस्तेमाल करना चाहते हैं तो आप वो भी कर सकते हैं ओपनली, कोई
यस
इशू नहीं,
सर।
लेकिन हम चूंकि यही इस्तेमाल करेंगे तो बेहतर है, आपको आसानी होगी समझने में।
ओके सर।
ठीक है, मैं अटेंडेंस का काइंडली वेट कर लें, मैं आपकी अटेंडेंस ले रहा हूँ 1 मिनट। Okay, your attendance will be in about, it will take about 4 minutes. So kindly stay online for 4 minutes and then you can leave the hall.
जी सर.
Okay.